Hello everyone. What we'd like to do today is unpack this thing called graduate attributes, which are generally ambitious descriptions academics use to frame the outcomes or objectives of any education program. They're a little like today's job descriptions. Beautiful, wishful lists of superhuman attributes, hence our picture. Okay, we're focusing on the engineering practitioner or graduate. Now, as we all know, in our rapidly changing world of migration, mobility, and globalization, society has become increasingly complex. Now, when we add the exponential development of all forms of technology, then work using these technologies in relation to society becomes extremely challenging. This is what engineering practitioners are expected to do: work at the interface of science, technology, society, and nature. It's worth noting at this stage something that all of you will recognize. Each of these disciplinary areas represents very different kinds of knowledge practices, and many STEM profession educators face the same challenge: how to enable graduates who can navigate and synthesize the different knowledge practices across different disciplinary spaces in different socio-technical contexts. That is at the heart of our problem space for today's presentation and discussion. Now, formal professions are governed by international bodies which dictate standards of achievement for specified professional categories. The reason is simple: recognition, or not, of qualifications across borders, what with increased globalization and mobility. Now, in the engineering profession, how students are trained for engineering work is governed for many countries by international accords and national professional bodies. Now, the engineering accords stipulate what they call knowledge, skills, practices, and values that are required to be eligible to become a professional. And this is where our problem starts. A typical bachelor's in engineering stipulates the achievement of these 11 what are now called graduate attributes, but used to be called exit level outcomes, more appropriately. And what one finds in South Africa, for example, and I believe in other cases too, is that each one of these graduate attributes needs to be assessed in a particular final or exit level module. Some modules, like design or capstone project modules, can have 2, 3, 4, maybe 5 of these so-called graduate attributes assessed. But heaven help you if you'd like to assess all of them in a large project, for example, taking a holistic approach. The long and the short of it is that these standards, international and national, and then qualification specific, tend to be treated like checklists, which are further reinforced when industry keeps publishing lists of top 10 skills desperately needed, ranked in order of priority. Now, despite the international standardization and detailed specifications and accreditation processes, global surveys confirm consistent skills gaps and shortages to tackle today's complex challenges. In other words, we as higher education are not meeting their requirements. Now, one of the problems, and this is begging for an autonomy paper, but not today, is the stakeholders in this space. When we talk about GAs, who is we? Higher education institutions, the International Engineering Alliance, academics, employers. So as part of the background study to today's presentation, we looked at a range of these stakeholders over a 30-year period to try to understand what each particular stakeholder means by a graduate attribute and how the focus has shifted over time. Now, the reason for the original study was the following problem. All these stakeholders produce lists which actually look like ingredients and recipes to make a cake. The problem is that the gap between the list of ingredients with its associated steps and the actual cake at a birthday party is becoming increasingly complex and nuanced. Whose party? What time of year? What ingredients are available? What are the cultural practices of the people at the party? What are the allergies? That is about knowledge practices in context. How can we expect educators to better meet the needs of employers and society if we keep using technicist checklists? Over the 30-year period that we looked at, we see significant shifts in what ends up on those lists. Just generally, starting with 30 years ago, very particular kinds of knowledge and technical skills with reference to engineering in particular. We then see a shift at the turn of the millennium to what was suddenly called generic skills. Then, when enough people jumped up and down to say, hang on, these things are not generic, they try to differentiate, and we see this in the literature, between generic skills meaning communication, teamwork, problem solving, etc., and so-called positive values and attitudes, consideration, respect, appreciation, etc. Then we see the next clear shift is this huge focus on employability and technological competencies. This is in direct response around 2010 to exponential technological developments, which graduates were simply ill-equipped to tackle in all fields. Today, we see increasing references to holistic graduate development. But all of these elements, what are called skills or practices, are still captured as lists. Now, anyone who has encountered LCT can already see the problem with lists, the lack of relational thinking. So, for the background study, we went back to the beginning. The term graduate attribute was coined by an Australian named Simon Barry, and he proposed a relational way of thinking about what we want of our graduates. He proposed a threefold stance. Our graduates need to develop a stance towards knowledge, towards themselves, and the world. Now, the puzzle pieces demonstrate the relationships between these three stances. For example, to conduct research or inquiry into kinds of knowledge means accessing, interpreting information from the world in ways that are representative of the appropriate or legitimated ethical, social, professional practices in a field. Engaging with this knowledge is dependent on personal, self-regulated or independent learning practices, which all entail forms of information literacy. All of this knowledge is decoded and encoded again in appropriate or legitimated communication practices back into the world. So, using that Sydney model, we then went through the lists over the 30-year period by these different stakeholders and allocated an orientation to something. What was that particular item on the list referring to? And we differentiated between scholarship, knowledge focus, lifelong learning, self-focused, and global citizenship, world-focused. We separated out communication because it's the thing that connects all of them. Now, what we see over that 30-year period across all those different stakeholders is an increasing focus over time on an orientation to self. And the descriptors become more and more nuanced and refer to innate, even pre-existing qualities. In other words, the graduate attributes over the last 30 years with reference to engineering have shifted from a knowledge to a knower orientation. Just by way of example, in the academic literature, we see teamwork shifting from the lower half in the early literature to the top in the latest literature. In contrast, we see technical competence shifting from the top to the bottom of the list in the more recent work. Now, employers have always listed more knowery attributes, but they've become increasingly nuanced dispositional qualities like empathy and resilience, passion, tenacity. How does one enable or elicit these dispositions against standardized checklisty qualification specifications? So, the focus for the paper is how do we help engineering educators to achieve holistic graduate attribute development in their students. Now, if we go back to the relational Sydney model, the concept of empathy, for example, requires awareness of self, other, and context, which is informed by access to and interpretation of kinds of knowledge, knowledge of self, knowledge of other, knowledge of context. Access and interpretation of these forms of knowledge requires information literacy practices to demonstrate your awareness. Remember, we're talking about empathy, both at the informal, intuition-based and formal scholarly level, relies on communication, whether verbal or physical, technical or even professional. So empathy starts with seeing and interpreting the world around you and locating yourself within it. That's just one example. I think what may already be quite evident is that the LCT dimensions can help us to problematize what we are terming graduate attributes and how to develop them relationally. I believe we can all see the obvious dimensions we could apply to the Sydney model to help educators see. Specialization is about making the distinction between what might be foregrounded in a curriculum, pedagogy, or practice, knowledge and knowers. I think a further distinction can be made, drawing on Bernstein, between repertoire and reservoir to differentiate between the knower, which is now sort of on the right-hand side, as individual, and knowers collectively in a field or social space. So given that we now have specialization as an overarching dimension, we can use its different planes in conjunction with the Sydney model elements to problematize and operationalize strategies to enable graduate attribute development. Semantics, naturally, almost acts as a different axis to flesh out developmental cumulative knowledge building for knowers. I'm going to showcase one example per plane to illustrate how LCT can be used to make sense of graduate attribute development. So the specialization epistemic plane is really useful for delineating the relationship between the what and how of any knowledge practice. Now, some of you might know we've used this plane quite extensively in our work on engineering problem solving and strategies to stretch students from fixed to more open-ended practices, to encourage students to engage with phenomena that range from well-known, well-bounded concepts to ambiguous or uncertain phenomena. Our colleague Carl Kruger has designed a student learning experience in his control systems course as follows, using the epistemic plane. So he aims to enable students to build on a solid foundational grasp of fundamental principles and associated procedures, in other words, scholarship, while addressing increasingly open-ended, real-world aligned engineering problems in different contexts. That's part of the world, the global citizenship. Now, by designing an iterative, developmental, and increasingly complex cycle around the epistemic plane, this is more likely to enable the basis of potential lifelong learning for the student, him or herself. That's our third pillar on the Sydney model. I've mapped the two processes, the two models next to each other. So here is number one. He starts in the real world, a context for a specific control problem, then moves to different examples from which he can enable them to elicit fundamental models. Then, with the purest insight, understanding fundamental principles, he moves them into interpreting and applying the fundamental principles of that model, which is about a relevant form of knowledge, the scholarship element, and they take responsibility for designing and appropriately visualizing, implementing the required information literacy communication practices in a particular solution. And this continues in an iterative cycle, becoming more complex as we go along. But Carl's approach is one way of seeing the relationship between the three graduate attribute pillars in the Sydney model. So what we're seeing here is a code shifting strategy that enables students to stretch their thinking. Now, if you add this cumulative knowledge focused approach into the pedagogical space, we can see the development of gazes. This is now the social relations plane. So we have a number of colleagues who have experimented with ways to further stretch students by, for example, developing repositories of case studies. Now, case studies expand the knowledge practice base. In other words, this is the scholarship in context element, and it exposes students to real-world engineers who are represented in these case studies. Now, when you couple this case study approach, which stretches the research and inquiries and information literacy side of the Sydney model, and you couple this with reflective individual and peer learning strategies, making use of supportive tutors and well-designed flipped classroom sessions, you are effectively developing the student gaze. Now, my colleagues Debbie Blaine and Melody Neves have implemented this in material science over a number of years. Now, if this approach is repeated, imagine Carl's cycle around the epistemic plane and this strategy for developing gaze. You will see that we're actually working on the student developing their personal and intellectual autonomy. Now, the dilemma with all those lists, and even the Sydney model, is the question of levels of meaning making. Semantics, as we know, is ideal to unpack how we enable cumulative knowledge building that can enable students to navigate the spaces between context independent or dependent and simple or complex. Now, one of our earliest papers described an approach to large class teaching where students were expected to calculate things like flow rate and head in piping systems, but when in fact they'd never even engaged with such a system in the real world. So Robbie and our colleague Neil Huissen implemented a practical group project designed to enable students to work with simple, concrete examples. They held a competition for groups to see who could get water piped up a tube outside the engineering building the fastest and the most efficiently. Now, each group got a bucket of motors, valves, pipes, etc. The intention was for them to experience flow rate in action. But the key feedback after the initiative was, in fact, all the know-y stuff to do with professional practices, teamwork, communication, etc. Now, anchoring their experience in the simple, practical, real-world space allowed Robbie and his colleagues to draw the parallel to more complex systems and, in an iterative fashion, very similar to Carl Kruger's epistemic plane curriculum design, they could weave the students around the semantic plane to develop increasingly complex knowledge practices. In summary, we are suggesting that elements of well-designed project-based learning opportunities probably go the furthest in covering the three graduate attribute pillars in professional education. What I have hoped to demonstrate is that by using Simon Barry's original model for graduate attributes as a solution to the graduate attribute lists problem, we can apply the LCT dimensions to operationalize how an engineering educator might go about enabling students to develop the holistic insights and gazes, as well as increasingly complex problem-solving practices implied by the different graduate attributes. We hope we've demystified the term graduate attribute by practically unpacking the difference between knowledge and knower elements, visualizing the intended outcomes as a function of actual classroom practice and curriculation. We believe that it is only by rigorously using such instruments as those offered by legitimation code theory that we can hope to address the ever-widening gap between higher education and employer expectations. Thank you very much.